Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem that is kind of complicated, but we're going to break it down into simple components. We have these three spheres here that are rotating about this ring G, but the ring is also going with the velocity to the right-hand side of this drawing. So the whole thing is spinning and going sideways like so. At some point though, the ring breaks and then these balls are free to move to different directions away from the ring. And what we need to find out are the velocities at the end when the ring breaks, and also this distance d. I'll read the problem statement, but before I do, let me show you a little animation. So you can see the ring, so it's spinning and also going to the right at the same time, but then the ring breaks at some point and the balls are now free to move away from that original ring G. Cool, so let's read the problem statement now and see what we're talking about. Three small identical spheres A, B, and C, which can slide on a horizontal frictionless surface, are attached to three 200 mil long strings, which are tied to a ring G. Initially, the spheres rotate clockwise about the ring with a relative velocity of 0.8 meters per second, and the ring moves along the x-axis with a velocity of 0.4 meters per second. Suddenly, the ring breaks and the three spheres move freely in the xy plane, with A and B following paths parallel to the y-axis at a distance of 346 mils from each other, and C following a path parallel to the x-axis. We are to determine the velocity of the sphere and of each sphere and the distance d. Okay, so what I'm going to do is I'm going to break this problem into two parts. In the first part, we're going to solve A. Okay, so we're going to be determining the velocity A, B, and C of each of the spheres. And then on the second video, I'll do part B. Okay, so then we can deep dive into the angular momentum part of things. So on this first video, we're only going to briefly think about angular momentum, and then on the second one, we're going to actually deep dive on it. Cool. So let's go about the problem statement one more time and identify some things that are important. The spheres are identical, right? So this is an indication that the mass of A is the same as mass of B, which is the same as mass of C. What else? They can slide on the surface without any friction, so it's a frictionless surface. So this is an indication for us that the conservation of energy can be applied at this point, because we're not losing any energy due to the friction between the surface and the spheres. They're attached to the ring G, they're rotating clockwise with a relative velocity of 0.8. So why is there relative velocity? Well, if you think about it, and I have a bigger drawing here, what's happening here is that this whole thing is moving. Think of this as one single block, okay? And this whole block is moving on this direction here. So the whole thing is moving to the right? But at the same time, the balls also have a velocity because they're moving about g. So each of them has also its relative velocity of 0.8, right? So and this velocity is always 0.8, and it's changing in time. Right now it's here, but then when A is over here, then it's going to be here. When A is over here, it's going to be downwards. When A is over here, it's over here. When A is down here, it's going to be leftwards, right? So the magnitude of this relative velocity is always the same, but the direction of it is always changing as my sphere A is rotating about g, right? Now, why is that important? Because when we think about linear momentum, right, the linear momentum of this guy is just a combination of the masses of the whole thing going to the right. That's all we have for linear momentum. Because what happens is the relative velocities about g cancel each other, right? So let's say that the left component of this velocity here is going to cancel out with some of the left component of this one at this instance shown, right? And afterwards, we can take this top here with the bottom component of A and also the bottom component of C. So this guy here plus this guy equals this guy, and this is what stops this whole thing going up, moving up or down, the whole system about g, right? So this is why it's important to think about relative velocity. The other thing is that because there is this v naught for the whole thing, if you actually take if you think about the absolute velocity of A, of one of the spheres such as A, what we need to do is we need to take this velocity and plug it in here and then combine the two, right? So it's going to be something like this, and the actual velocity vector for A, right? If we take vector for A completely, this would be it, right? This red one here, which is combining this one here from the whole thing and this one here, which is a one just for A. So that's why it's relative velocity of A. So when they say it's what was it that they said? I think 0.4. Yeah, 0.4. So this guy here, so it's saying that this guy here, only this guy here, this guy is 0.4 meters per second, and they're only giving magnitude because this is always changing directions. Okay. What else? It's moving along the x-axis, and the velocity v naught is 0.4 I. And this I is just an indication, right, that this guy is moving on the along the x-axis and on the positive direction of the x-axis, which is considered to be the right-hand side, just by convention. Okay, so this I is just indicating that it's going this way here, such as a figure. Suddenly the ring breaks and the spheres move along parallel paths. Okay, great. Awesome. So now what we need to do is we need to find the velocities after the ring breaks. So we need to find velocity A, B, and C. How are we going to do that? Well, we're going to apply the conservation of linear momentum and the conservation of energy. That's all. Okay, straightforward. So let's start with the linear momentum. Like we were just discussing, the linear momentum, the only linear momentum of this whole thing is, before the whole thing breaks apart, right, is this system, if you will, or this block with the three masses going rightwards with a velocity of v naught. It's not going upwards, it's not going downwards, it's not going backwards, it's only going rightwards, because all the relative velocities are canceling each other, and we're left only with this v naught velocity for the whole thing, for the whole system, right? So if we write that down, if we're going to write down, let's put here linear momentum, and we write our momentum before. So before, what do we have before? Well, before we have the mass of the spheres, and the three masses are the same, right? So we can say it's remembering that our momentum is mass times velocity. It's the simple definition of momentum. So before momentum is just the v naught times the mass of A plus the mass of B plus the mass of C, right? What about the afterwards? So let's put it here. Afterwards, after ring breaks, that is. Then what is our linear momentum? Our linear momentum is the combination of the individual spheres, right? So we have, what do we have here? We have these guys here. Don't need this for now. Nor this, nor this, nor this. This is for the next video. What do we have? Well, we have this situation here. So we have the velocity of A going upwards on the y direction. We have C going rightwards on the x direction, and we have B going downwards on the y direction. We might as well just define, for the sake of not confuse ourselves, that we're considering rightward to be positive and upward to be positive as well. Okay, so what do we have afterwards? Well, we have the mass of A times times the velocity on the y direction. We have the mass of C times the velocity on the x direction, and we have the mass of B times velocity. So you can see already that these two guys cancel each other, right, in terms of linear momentum, right? And because they have the same mass, we can already expect them to have exactly the same velocity. What about this guy here? Well, this guy here has to have velocity related to the original velocity of the whole system, right? So what do we have afterwards? What do we have afterwards? So afterwards we have, I should have said, I should have broken down this before. So this is on the x direction, okay? So the x-axis, or horizontal, if you will. Okay, so we're looking only at the horizontal. This is horizontal movement. This is horizontal movement. So what do we have on the horizontal? Let me go ahead and put an x here just for the sake of it. Okay. So what do we have afterwards? We have the mass of C times the velocity of C, right? Because mass of A, what's the velocity of A on the x direction? Nothing. What about B? Nothing on the x direction either, right? So if the conservation of momentum, if it has to be respected, so if the delta P is 0, then that means that my V naught times the three velocities, the three masses are exactly the same. They are identical here. So 3 mass has to be equal to the mass of C times velocity of C. Now, mass of C is the same thing as the mass before. It's the same mass. So therefore, that means that. So therefore, VC is just 3 times V naught. And V naught is 0.4. So therefore, VC is 3 times 0.4, which is 1.2. So that is very straightforward and easy to do. Yep. Cool. So that's velocity VC. That's one of the answers we're looking for. What about if I copy and paste this, but we do this on the y direction now. So let's do the same thing, but now on the y direction. So linear momentum, but instead of doing it, let's do it in the vertical. Okay, so what do we have before on the y direction? Nothing, right? Remember we talked about this. Everything is canceling each other, so that's why this guy's not going up or down. It's only going rightwards. So that means that before we have the mass of everything, 3 times masses times nil times nothing. So this is nothing. What about afterwards? Well, afterwards we do have some things going vertically. Sorry, A and B. A is going on the positive direction, and B is going in the negative direction, right? So therefore, linear momentum here, linear momentum in the y direction is going to be mass of A times velocity of A minus mass of B, velocity of B, because it's going in the negative direction. And we can also put here, if we want, mass of C times velocity of C on the vertical direction, which is 0, so it goes away. And then once again, if we say, okay, so the conservation of linear momentum applies in this case, there's no external force, so therefore 0 has to be equal to the mass of A times velocity of A minus the mass of B times the velocity of B plus 0, and therefore the mass of A times velocity of A has to be equal to the mass of B times the velocity of B. The masses are exactly the same. They are identical spheres, so therefore the velocity of A has to be exactly the same as the velocity of B, right? So we just prove mathematically what we could see intuitively before. Okay, so just know that this is magnitude, right? Because we set the directions from the start. We said already that B was going downwards and A was going upwards. So just remember this is just valid for magnitude, because we know that in reality they have opposite directions. Cool, so we have two unknowns. We use two equations. We use the horizontal direction for one of the unknowns, and then we use the vertical linear momentum for another one, and now we have still one unknown to solve. So we need one more equation. We're going to use conservation of energy. And the idea here, well, same as always, right? So there should be no change in energy if we're not losing any energy to the friction to the surface. So therefore, our before and after have to be the same. What do we have beforehand? Well, beforehand we have a lot of motion going on, right? We have the motion of, so before we have the motion of the whole system. Where are we? Here we are. We have the motion of this whole system going this way, but we also have the individual motions. And in this case, there's no canceling out because we don't have, negative motion versus positive motion. We don't just have motion. So in this case here, we actually have the motion of these guys, the relative velocity they have as they're spinning about g, and we also have the whole thing as it's going rightwards. Let's see the video once again, just to be sure. So they're spinning, and they have all the kinetic energy relates to the motion rightwards plus the motion as they are going about g. Okay, so there's two ways you can go about computing this when we're doing the calculation. One way, which I guess is the hard way, is to do what we talked about before and get this vector here, place it here, and then combine the two to get the vector for velocity a, let's say the absolute velocity for a, and multiply by the mass of a. So we're going to get the kinetic energy for a, and then we can do the same thing for c, right? We can get the same vector v naught. Where is my v naught? Let me just grab v naught. Do the same v naught. Some of them cancel each other out. There you go. Boom, and then our vector is going to be the combination of these two, and we can do the same thing here for b, and then combine it like so. And combine it like so, right? So this would be, my velocity b. We can multiply that by the mass and get the kinetic energy, and also get my velocity c, and combine it to get the mass and kinetic energy of that. So that will be the harder way. The other way to do it is, since you already have these two vectors broken down, so we have this one and we have this one, we can do it for the whole thing. And I think that's the easiest way to do it. So what do we have before? Well, before we have, the whole system moving rightwards. So that would be 3 times my mass times my v naught, which is 0.4, right? And that's squared over 2. And then I also have the individual masses. So I have the mass of A times its relative velocity of 0.8, and that's squared over 2. And I also have my mass of B, and this is not going to be enough space. My 0.8 squared over 2, and my mass of C, and the 0.8 squared over 2. Okay, so that's what we would have before the ring breaks. But then after it breaks, then we don't have that motion anymore due to the ring, right? We only have the motion of the individual spheres. So what do we have afterwards? Well, then afterwards what we have is, the mass of A times its acquired velocity squared over 2, plus the mass of B, its new acquired velocity over 2, and mass of C over 2, right? And all the masses are the same. They are all identical spheres. Everything has 2 dividing, so we might as well, because we're going to apply this, we might as well simplify things. And then I'm going to remove every instance of mass, and I'm also going to remove every instance of 2 that we have. And this, I'm going to make the 2 things equal, because we're not losing any energy. So this is going to be 3 times, right, 0.4 squared, plus, this is 3 times mass, right? Or in this case, because we're removing the mass, it's 3 times the 0.8 squared. So 3 times my 0.8 squared has to be equal to my VA squared plus my VB squared plus my VC squared. And we are 100% capable of solving this equation, because after all, we have the magnitude of VC. We calculated that already. And we also know that VA and VB are the same, right? We know they have the same magnitude. So in other words, this is 1.92, this is 3.48. These 2 guys combined, so this is the same thing as 2 times VA squared or VB squared, doesn't matter. And then over here we have also the magnitude of C, which is 1.2 squared. Okay, so I can solve this by, sending this 1.44, subtracting over there, dividing everything by 2, and taking the square root. So that means that VA is just going to be the square root of 192 plus 0.48 minus 1.44 divided by 2. And this gives me 693. It's 69282, but 693 is good enough. It's approximation. Cool. So what do we need? Does it matter whether it's positive or negative? Oh, not really, because we know the direction already, right? We know that the A is going upwards and VB is going downwards. So if you were to write this, because you know this already, then we would write like so. So V separated into 2. So my VA equals 0.693 meters per second, and it's going upwards. And my VB is minus 0.693 meters per second. And we know that it's going upwards. And this is the answer for part A. So we just got the velocities for all of them. So note that first of all, what happened with velocity C, remember that C had 1.2, right? So what happens with velocity C is that it takes the original linear momentum before the ring breaks, and it converts everything into the velocity of C, because A and B don't have any of that right hand movement, right? So none of them are going horizontally rightwards. So that means that this guy here has obtained all the momentum of the whole system that was going rightwards before. And that's why it's 3 times faster than the original velocity. The original velocity was 0.4 meters per second going rightwards. And now because we had 3 masses going rightwards and now we only have 1, then this guy now is 3 times faster because the linear momentum has been conserved, right? Now, what about these 2 guys here? Well, these 2 guys here, they are going on opposite directions, and they have the same magnitude, or else we'll be creating linear momentum going upwards or downwards, right? So they have to be equal in magnitude. So what happened with them is that the kinetic energy, right, the kinetic energy that was related to the whole thing moving both around G and going rightwards, was converted into only one direction motion for each of them. Okay, so this one ended up being 0.693, and this one ended up being 0.693 as well. So this is the first part of the problem. Now, to be able to solve the second part, which is finding out what this distance here is, what we need to do is we need to use the angular momentum. So we need to use the conservation of angular momentum. And because I want to, take a bit more time to explain different possibilities here, I'm going to make a separate video so that we solve part B. Okay, so part B is coming up on the next video. If you have any questions, as per usual, let me know. Happy to help out, and we'll talk soon.